I'm going to be speaking a bit about industrial heat pumps. More specifically, it's the technology I focus on the most in my role, and I find that it serves as a great proxy for transforming the market as the most efficient electrified technology that's available in a lot of cases. So there's significant process heat demand at low and medium temperatures. Technology is ready to meet it. Recent work reinforces that much of the opportunity is technically feasible. So what makes a site a slam dunk for industrial electrification? It's the confluence of these factors. So where energy savings meets economics, meets corporate goals, meets thermal redesign. Uh, yeah, it's energy savings, high coefficients of performance. That's the energy delivered to the system over the energy input to the system, high efficiencies, waste heat recovery first, of course, simultaneous heating and cooling, being able to create closed loops and systems all increases the potential energy savings. Corporate goals and ESG targets, clean energy targets. Companies that are prioritizing electrification will always make a site more attractive for an electrification project. Also, when sites are subject to regulations, so regulatory factors can also increase feasibility. The economics, so the spark gap that we just talked about, where it's as favorable as possible, the opportunity to leverage financing. So in the US, that's federal and state utility, and also the opportunity to save costs through co-benefits, which I'll talk a little bit more about in a couple slides. And then there's the opportunity to redesign process, especially in greenfield facilities, we found to be a great opportunity for electrification. But we've also found that with traditional boiler engineering, sites over-design and overcompensate and design for the highest thermal quality needed rather than the lowest needed, and use heat pumps to boost in those applications where it's truly needed. And then there's the opportunity to avoid lock into really long boiler timelines, natural gas and fossil fuel-based infrastructure that becomes very difficult to dislodge economically. So some examples are dual loop systems, co-located systems, waste heat recovery opportunities, process heating operations greater than 4,000 hours a year. That's where you get the highest efficiencies, where heat pumps are working and working and working. Water heating for pasteurization, drying, preheat or sanitation water, food processing, pulp and paper, breweries, ethanol, things like that. So I think what this slide mostly covers is that the market isn't binary between yes or no. Can this happen right now? It's segmented between various buckets. Some projects work today, some need coordination, some need policy, and some need innovation. So you have a bucket one of no-brainer projects, financially feasible today, the ones that Eric talked about, where there are co-located sources and sinks, favorable spark gap, efficient, easy to construct. Those are hard to find. Excuse me. And then you have here bucket two, let's find a way, where great coefficients of performance take projects to the fence line, and then funding programs or policies exist to make projects feasible and actionable. And what's still needed are utilities, funding program connections, feasibility studies. And you have the third bucket where policy support is needed, where projects are limited by major barriers, constraints on fuel switching, spark gap, and what they need is effective policy mobilization to support potential end users, to develop utility and state programs, whatever it is. And then you have the fourth bucket, which are those that are not yet viable, where economic constraints are too limiting, the technical capacities are not there, and that's where we need RD&D, advancing of manufacturing of technologies to improve capacities and temperatures and things like that. Industrial heat pumps and thermal batteries are currently deployed in the United States. They are still a nascent technology, but they do exist. This map that ACEEE developed shows where those technologies are in place, where they're planned. Some of those planned projects are supported by federal funds, the status of which is a little bit unknown. Some of the co-benefits, those that accrue to the facility, those that accrue to the system, those benefits are real, but they're rarely monetized in capital decisions, and they just become a part of that value proposition. There are things like insurance savings, reducing maintenance costs in some cases, resource conservation. So water that might otherwise have to go to cooling towers can discharge its heat and be used with a heat pump that can be recovered. Permitting ease when you're removing combustion potentially from a facility. Your future-proofing and increasing the modularity of your process. And then some of the system level benefits, things like air quality, removing pollutants, creating jobs, reducing noise pollution, uh, increasing the health of the workforce. So if we only compare fuel prices, we definitely miss value. This slide just simplifies the value proposition. The costs of electrifying on the left and what they're offset by on the right. So the cost of electrifying the CapEx, the new equipment, that can be significant. So can process downtime. Absolutely. When we're talking about installation and integration, the amount of downtime that a facility has to incur to install new technology can be significant. And the costs of installing and integrating, we've seen in some cases, can be as high as 3 times the actual CapEx itself. So there's the need for supporting infrastructure as well, talking about electricity, new transformers, things like that. And then, of course, there's the spark gap or the OpEx. And what that ends up being offset by or needs to be offset by are the efficiency gains. So the coefficient of performance, again, financial support, wherever that can come from, innovation grants, federal grants, state programs, utility incentives, whatever it is. And then there's the ESG air pollution compliance side of things as well. And then there are those co-benefits. And so what this combines to is figuring out exactly what the payback is and finding out how actionable a project is and what other resources need to be mobilized to drive down that payback to the greatest extent possible. So here I have an example deployment of a business case. We don't have to go too into the weeds here, and we definitely could, but let's say there's a brewery that aims to reduce its Scope 1 emissions and on-site natural gas use. It might anticipate some new regulations coming down the pike. They've done an assessment that reveal a bunch of opportunities for low-cost efficiency improvements. And let's say they've identified an industrial heat pump that can recover waste heat from work cooling at 85 to 90 degrees C and use it for hot water processes. So that would reduce the brewery's use of steam from its natural gas boiler. The first step here is technical validation, some kind of energy assessment. Obviously, this differs depending on where you are and the size of your facility, but things in the US from like an industrial technology assessment center, sometimes utilities provide energy assessments. That's the first step. They identify what the opportunity is. They identify the energy reduction potential. They identify the technology and the potential coefficient of performance. And then the next step is the business case development. So using a state cost share feasibility study, for example, using the tools and resources that are available on the market to send out quotes to industrial heat pump suppliers or other electrified technology suppliers, identifying what that payback might be. In this case, let's say it's 4 to 6 years, but there's this new load that's added as well, new transformers required. That's part of the business case. And then there's the ecosystem engagement. So coordinating with the utility account manager, determining how much of the project state funding might cover. Let's say it's 60 to 65%. This is a great project. Utility custom incentives. So stacking the potential funding opportunities together and figuring out how much of that total cost can be offset, all leading to coordinated implementation and data sharing. This is an extremely simplified view of how the process that a project might take, but this is an overview of a business case and the steps that it needs to proceed down to move towards implementation. And then, of course, there are still remaining barriers to industrial electrification, and there's action possible from the end user perspective is what I've tried to highlight. There's the well-known barriers, and then there are some understated structural barriers that I've encountered in trying to engage in technical facilitation with facilities. So on the left side, on well-known, there's the upfront capital, there's the spark gap, and things that end users can do, project bundling, stacking incentives, looking at a lifestyle cost framing, and figuring out what the internal ROI is when you're talking about future-proofing a facility and building towards more holistic electrification. There's definitely perceived technology risk throughout the market. There are a number of deployments and projects in countries around the world. In the US, they're a little bit limited. The performance data, there's still a need for pilots. Case study sharing across peers, peer exchange networks are great. There is the utility interconnection and grid constraint problem, of course. And that's why it's important to engage utilities early in the design phase and not after engineering. Once you have blueprints drawn up, it's a little bit late. And then there's the supply chain and lead times, and that's going to differ depending on who and where you are. But integrating electrification into your long-term capital planning cycles is how that can be overcome to some extent. In the US, for example, lead times have dropped as the market has developed from around 24 to 36 months to, I would say, 18 to 24 today. And there's some understated structural barriers as well. There is some corporate versus facility misalignment, where corporate structures are really interested in decarbonization and facility managers are less informed or less plugged in or have less time to engage in, relatively nascent technologies and how to deploy them. And so building internal coalitions early, engineering, finance, sustainability, bringing those pieces together is really important. And that pairs with budget timing and downtime windows, where corporate entities often have budget timings that allow them to make their decisions on very particular bases. And that doesn't always line up with funding opportunities that are, if a state comes out with a funding window that gives 3 months to apply, that might not line up with when a company makes their budget decisions for the coming year. So aligning electrification with planned maintenance cycles, planning ahead to the greatest extent possible, and from the state and financial institution perspective, being flexible with the opportunities. There's complexity with incentives and tax credits. And that's just going to be the way to move through that is to designate internal or external expertise to navigate those opportunities. And then there's electrification as load liability. And the action there is to quantify the flexibility potential, thermal storage, and demand response in proposals.